In this module, we'll cover wireless LAN security. So wireless LAN security is a heavy topic, but we'll start from the early days. And with that said, we'll address legacy Wi-Fi security. After that, we'll get into the current Wi-Fi security methods. That's followed by wireless LAN guest access. And then we'll cover mobile device management, or MDM. And that's followed by Hotspot 2.0 and Passpoint. And then we'll cover network segmentation. And finally, we'll address network access control, or NAC. So let's get started. So in this first section, we'll talk about legacy Wi-Fi security. So what we mean by legacy Wi-Fi security is some of the security methods that we used in the past that are either no longer used or have been compromised, or both. And we'll start with Wired Equivalent Privacy, or WEP, and Temporal Key Integrity Protocol, or TKIP, Wi-Fi Protected Access version 2, or WPA2. WEP is a security algorithm presented by the IEEE as part of the 802.11 Internet Standard that was ratified in 1997. Now, WEP was created to secure and ensure data confidentiality at the same level that a traditional wired network offered. And wireless connections transmit data through radio waves that can be intercepted, of course, and WEP was designed to encrypt this data so that even if it were to be intercepted, such as a man-in-the-middle attack, the threat actor would not be able to decipher its contents. That was the theory. Now, WEP uses the ARC4 streaming cipher for confidentiality and the CRC32 checksum for integrity. Well, what is ARC4? Well, ARC4 is an encryption algorithm that uses a variable length key to generate a stream of pseudo-random bytes, and it's used to encrypt and decrypt data, but it's not as secure as some other algorithms that are available today. Now, stations connected to this Wi-Fi network using WEP can exchange encrypted messages. The 64 WEP key uses a string of 10 hexadecimal alphanumeric characters, while the 128-bit WEP uses a string of 26 hexadecimal alphanumeric characters. Now, these characters are either numbers between 0 and 9 or letters between A and F. Now, the three main goals of WEP encryption were confidentiality, access control, and data integrity. And the primary goal of confidentiality was to provide data privacy by encrypting the data before transmission. And WEP also provided access control, which was a crude form of authorization. And client stations that don't have the same magic WEP key as the access point are refused access to network resources. And the data integrity checksum, known as the integrity check value, or ICV, is computed on data before encryption and used to prevent data from being modified. And WEP uses an initialization vector, or IV, as part of its encryption process. And the 64 WEP protocol used a 40-bit static key combined with a 24-bit IV, while the 128-bit WEP protocol used a 104-bit static key with a 24-bit IV. And the IV was sent in clear text, which means that an attacker can intercept it and perform a replay attack. And in addition, there's only a limited number of possible IV combinations, which means that they could be reused, and this makes the encryption vulnerable to attack. And as a result, WEP is no longer considered a secure method of encryption. Now let's move on to Temporal Key Integrity Protocol, or TKIP. Now, TKIP was developed as an interim solution to overcome the limitations of the outdated WEP protocol. And TKIP was introduced as a quick fix to improve the security of existing Wi-Fi networks while providing a robust solution. So to understand how TKIP works, let's take a closer look at the frame composition. Following the MAC header, the frame includes the IV, which is the initialization vector, and key ID, which are used to generate encryption keys or data protection. The extended IV is an additional component introduced in TKIP to increase the security level. It helps prevent replay attacks by ensuring that the IV values used in encryption are unique for each frame, and the data section of the frame carries the actual payload, which can be user data, control messages, or management information. Now, the MIC, or Message Integrity Check, is a cryptographic checksum calculated over the frame data and ensures that the frame has not been tampered with during the transmission. The WEP-ICV, or Integrity Check value, is another checksum that's added to the frame. Now, while WEP-ICV was not part of the original WEP protocol, it's still included in TKIP frames for compatibility purposes. And then finally, the FCS, or frame check sequence, is a checksum calculated over the entire frame, including the MAC header, data, MIC, WEP-ICV, and other components. And it provides a means for error detection and ensures the integrity of the frame during transmission. Now, in TKIP, we take the initialization vector, or IV, and extend it to 48 bits. And this IV serves as a sequence counter, starting from 0 and incrementing by 1 for each MPDU. And to strengthen security and eliminate weak keys, we introduce an additional 32 bits to the original 24-bit IV from WEP. But we intentionally leave 8 bits unused, and this is known as the WEP seed, to ensure that we get rid of those weak keys. Now, for proper sequencing, we rely on TSC1 and TSC0. These are temporal sequence counters, which are the lower IBs responsible for the sequence numbers. Now, during TKIP Phase 2 mixing, these lower IVs play a crucial role. Also, we have TSC2 to 5, the upper IVs, which increment by 1 after the lower IVs rotate. And these come into play during Phase 1 and contribute to the overall sequence numbering process. Now, the primary weakness lies in TKIP's use of a static encryption key, which allows for cryptographic attacks, and the lack of forward secrecy makes TKIP susceptible to key recovery attacks, where an attacker can exploit weaknesses in the encryption process to retrieve the key and decrypt the data. With forward secrecy, each session or communication is encrypted using a unique ephemeral key that's generated for that specific session. So now let's move on to WPA2 Personal. Now, Wi-Fi Protected Access 2 is based on Robust Security Network, or RSN, capabilities, and it was introduced by the Wi-Fi Alliance as an upgrade to WPA, otherwise known as TKIP, and provides stronger security for wireless networks. Now, WPA2 certification is based on the 802.11i amendment, which defines security mechanisms to protect wireless networks. And all Wi-Fi WPA2 certified devices must support CCMP AES dynamic encryption methods. And AES is a symmetric encryption algorithm that's used to encrypt data, while CCMP is a protocol that provides message integrity and confidentiality. WPA2 supports backwards compatibility for legacy encryption methods such as TKIP and WEP, but these methods are outdated and shouldn't be used. Now, WPA2 has two methods for user and device authorization for wireless LANs: WPA2 Enterprise and WPA2 Personal. And WPA2 Enterprise requires support for 802.1x port-based access control security, and is intended for enterprise deployments. Now, WPA2 Personal uses a less complex passphrase, and that's intended for home use, although some enterprise still uses WPA2 Personal. WPA2 Personal is based on PSK authentication, which uses a pre-shared key to authenticate devices on the network. Now, in the real world, most enterprise deployments still use WPA2 as the accepted level of security for Wi-Fi. Now, while no security protocol is completely foolproof, WPA2 AES provides a strong security for wireless networks by using a combination of authentication and encryption. but it was eventually proved vulnerable and was replaced by WPA3. So the encryption exchange, as we can see in the image, is where the AP sends an A nonce, which is an access point nonce, to the client. The client sends to the AP his S nonce with a mic, and the mic is mainly for the AP to recognize that this message is really from the client. The AP then generates a PTK, which is a pairwise transient key, based on the A nonce and the S nonce, and the pre-shared key. The AP then sends the GTK, which is a group transient key, to the client, which will be used to encrypt broadcast and multicast frames. The client then sends an acknowledgement back to the AP to confirm that it received the GTK. So let's look at this from the entire frame's perspective. We start with the MAC header, which contains important control and addressing information for the transmission. The data payload, known as the plain text data, is then encrypted using the CCMP algorithm. Now, as part of the encryption process, the CCMP header is created, and it includes fields necessary for encryption, such as the packet number and the key ID. Now, additionally, the CCMP header incorporates the encrypted mic, which is a value calculated over the plain text data. And this encrypted mic helps to verify the integrity of the data during transmission, protecting it from tampering. And to enhance security further, additional authenticated data, or AAD, is constructed, which includes relevant information like MAC addresses of the source and destination devices, packet number, and other required fields. Now, the AAD is used in the CCMP algorithm to provide additional authentication and integrity checking, and to generate unique encryption keys for each packet and prevent replay attacks. A nonce is constructed. The build nonce combines the packet number, the transmitter MAC address, and the key ID. The nonce value is then used in conjunction with the encryption key and other data to generate unique encryption keys for each packet. Replay detection is another important aspect of this puzzle and ensures that duplicate or repeated packets are not accepted and processed by the receiving device. And by keeping track of packet numbers and detecting any replayed packets, this mechanism prevents attackers from retransmitting captured packets to deceive the network. Now let's move on to WPA2 Enterprise. But before we go too far, I thought it'd be best to define some terms. Now, in a Wi-Fi network, the 802.1x protocol is used for port-based network access control and provides a method for authenticating and authorizing devices or users before granting access to the network. Now, in this framework, there's three key components. That's the supplicant, the authenticator, and the authentication server. The supplicant, in simple terms, is the user or device seeking to connect to the network. It initiates the authentication process by sharing its credentials or digital certificates to prove its identity. It's essentially the one asking for access. The authenticator acts as the intermediary between the supplicant and the authentication server. It is typically a network access device or an AP responsible for receiving the authentication requests from the supplicant and forwarding them to the authentication server. Now, the authenticator ensures that the network's authentication and authorization policies are followed, serving as a gatekeeper that determines who gets in. Lastly, we have the authentication server, which serves as the central authority in the authentication process. Now, it's a specialized server dedicated to authentication tasks, and when the supplicant sends its credentials, the authentication server verifies its validity. Now, this may involve validating usernames and passwords or verifying digital certificates. The authentication server communicates the results of the authentication process to the authenticator, which in the Wi-Fi case is the AP, which in turn makes the decision to either allow or deny access to the supplicant, and it acts as a final decision maker in granting network access. WPA2 Enterprise uses AES encryption to ensure that any data transmitted over the network is secure. The radius server is responsible for authenticating users, while the gateway APs send authentication messages between the supplicant and the authentication server. The APs convert EPL exchanges to radius access request messages, which are sent to the radius server's IP address and UDP ports specified in the dashboard. WPA2 Enterprise is typically used in corporate and educational environments where security is of the utmost importance. It's also suitable as an alternative for devices not compatible with 802.1x, such as game consoles in student dorm. And with WPA2 Enterprise, each user has their own unique login credentials that are authenticated by the radius server before they are granted access to the network. Most EAP types rely on a server-side digital certificate to validate the authentication server. This certificate, sitting on the radius server, undergoes verification by the supplicant's root certificate held by the client device, as we mentioned. And through this process, the supplicant ensures the authenticity of the server-side certificate, establishing a secure connection. Now, there's a number of EAP methods, and most EAP types rely on a server-side digital certificate to validate the authentication server. This certificate that sits on the radius server undergoes verification by the supplicant's root certificate held by the client device. And through this process, the supplicant ensures the authenticity of the server-side certificate, establishing a secure connection. Now, during the EAP exchange, not only does the certificate verification take place, but it also triggers the creation of an encrypted tunnel called the Secure Sockets Layer, or SSL, or Transport Layer Security, or TLS. And this tunnel serves as a protective shield, safeguarding sensitive information exchanged during the authentication process, such as the supplicant's username, password, or client certificate. And tunneled authentication is a common practice in many secure EAP implementations. And by employing the SSL TLS tunnel, the integrity and confidentiality of user credentials are fortified. And this added layer of security ensures that the authentication exchange remains private. The chart that you see here lists the different EAP types along with their respective methods, being client-side certificate required, server-side certificate, or both. The number of EAP exchanges depend on the EAP method employed. So here we show the EAP TLS exchange from a high level. And I'll begin with going with the step numbers as you can see in the diagram. So step 1 begins where the EPL start message acts as a trigger indicating the client's intention to authenticate and initiate communication with the AP. And in step 2, the AP then requests the identity of the supplicant with an EAP request identity message. In step 3, the station responds with its username. And in step 4, the access point sends an access request to the authentication server. Now this message contains information about the user attempting to connect, initiating the process of user authentication and authorization to gain access to the network. In step 5, a radius access challenge from the authentication server happens to request the client to provide further authentication data or respond to additional security challenges. In step 6, the authenticator passes on the EAP challenge request to the client. Now this message typically includes a challenge or random value that the client needs to use in the authentication response. In step 7, the each challenge response message is sent back to the authentication server, where the server evaluates the response to verify the client's credentials and determine if the authentication is successful. In step 8, the client's challenge response is then passed on by the AP as another EAP challenge request. The authentication server then processes the EAP challenge response. In step 9, the authentication server validates the client's response and responds with a radius access accept message that indicates that the client's authentication was successful and grants permission for the client to access the network. In step 10, the AP passes on the EAP success message to the client. And finally, in step 11, the four-way handshake then takes place.